So welcome to the online causal inference seminar. This week, we're very fortunate to have Colin Fogarty from MIT, who will talk about prepivoting in finite population causal inference. I think this is a joint work with his student, Peter Cohen. I think Dominic would explain how the Q&A works for today.
Yeah, as usual, please submit your questions in Q&A. We don't have a collaborator in Q&A today, so what we're going to do is we're going to either read your question to Colin, or if we have more time, we will unmute you and you will be able to directly discuss your question with Colin. If you participate during this seminar, please keep in mind that the talk will be recorded. Yeah, that's all from our side. Colin, yeah.
All right, well, thank you very much for the invitation to give this talk. So my talk today is on prepivoting and finite population causal inference, and this is joint work with my doctoral student, Peter Cohen. So I want to begin by maybe jumping back in time to the 1920s, 1930s, when Neyman and Fisher were embroiled in a fairly acrimonious debate over what notion of no treatment effect should be preferred. Now, a definition attributed to Fisher is that when we think about what does it mean for a treatment to have no effect? Well, in Fisher's mind, that meant that the treatment should not have an effect for any individual in the study. And this notion of no treatment effect has come to be known as Fisher's sharp null. Let's contrast this with Neyman, who thought instead that, well, maybe when we think about a treatment having no effect, maybe the treatment affects some individuals positively, some negatively, but that we should be interested in seeing if, on average, the treatment has no effect for any individuals in the study. So obviously, the truth of the sharp null implies truth of the weak null. But more importantly, these different operational definitions of no treatment effect give rise to very different modes of inference. Under Fisher's sharp null, randomization alone provides this reasoned basis for inference and gives rise to hypothesis tests that look a lot like permutation tests. We'll call it randomization tests, such that if one assumes the sharp null, one can get inference that's exactly level alpha for any sample size. Now, proceeding under Neyman's weak null, we instead get to tests that look a lot more like the usual large sample tests, say compute-Z statistic, look at a normal approximation, things of this sort. So there are a lot of philosophical reasons why one might prefer Neyman's null over Fisher's null and vice versa. It's certainly contentious then, remains contentious now. There's a nice blog post by Andrew Gelman if you're curious. And also, as an advocate of Fisher's null, a lot of Paul Rosenbaum's work in his textbooks has been very articulate in its support of Fisher's sharp null. But the main focus for me today is going to be on whether or not this distinction has practical implications. So as I said, really, randomization tests can provide exact tests for sharp null hypotheses. And broadly, these are hypotheses, as I would say, impute the missing values for the potential outcomes under their truth. So the concern we're going to be focused on today is whether or not randomization tests of sharp nulls are prone to misinterpretation by practitioners. That is, suppose a researcher kind of hears all these nice things about Fisher's sharp null, about randomization tests, about this exactness property, and wants to proceed using one. But then after using a test of the sharp null, thinks that she or he has evidence for the existence of a positive average effect if it rejects. In other words, interpreting the rejection of the sharp null as the rejection of Neyman's weak null. So suppose the practitioner actually has in mind the null hypothesis of the sample average effect equals 0, but does so using a Fisher randomization test, which we know is valid for the sharp null. So a seemingly innocuous choice of test statistic for this, if I really wanted to be focused on Neyman's null, would be to do a randomization test based upon the treated minus control difference in means. So assume the sharp null holds, enumerate the randomization distribution for the treated minus control difference in means. Unfortunately, that test, that Fisher randomization test, need not provide a valid test for the weak null, even asymptotically. So even the seemingly benign choice of test statistic, the treated minus control difference in means, if I use a Fisher randomization test based upon that test statistic, can give me invalid inference asymptotically. So a recent literature has really tried to address some of these issues. It's tried to focus on developing randomization tests that are simultaneously exact under Fisher-Sharp null, but also asymptotically conservative under Neyman's-Weak null. And this conservativeness is not like a deficiency in the tests in any ways, rather it's a fundamental property of inference under the finite population model. And in this talk, I'll kind of highlight why this comes up. So while the sharp nulls and weak nulls are different, these kind of randomization tests that have this robustness property to the weak null kind of obviate the distinction for practitioners. So that if a practitioner uses a Fisher randomization test based on one of these test statistics, they'll also be entitled to that conclusion pertaining to the average treatment effect. So there's been a literature on this developing, and a related literature has also developed in the context of permutation tests. So I'd say that said, the existing literature really provides resolutions on a case-by-case basis. So what I mean by that is, for a particular experimental design, let me try my best to develop a test statistic that retains validity under the weak null hypothesis. So an objective of this work was to try to take a step back from this really kind of bespoke case-by-case approach and really give a general methodology, a big hammer for providing this resolution. So the resolution I'll provide precisely recovers every known correction, every known resolution that I know of, and furthermore provides new unifications in situations where the existing fixes can fall short. So before diving into the details, I want to give you a loose sense of what the proposal is before we really dive into the nuts and bolts. So kind of the ingredients you need. So let's suppose that we begin with a candidate p-value that provides asymptotically conservative inference under heterogeneous effects. So maybe a large sample p-value that I know is conservative for the weak null, but that furthermore is consistent in level under constant effects. So if effects are truly constant, say if the sharp null holds, then the inference will be exactly level alpha. So what we'll then do in the usual framework, if I'm just testing the weak null, of course, I would just compare that p-value to alpha to make my conclusion. What we will do instead is to construct the randomization distribution under the sharp null of 1 minus this asymptotically valid p-value. So we're going to use 1 minus the p-value itself as a test statistic within the randomization test. So we'll be enumerating this randomization distribution, assuming that the sharp null holds. So that is, instead of comparing the p-value to alpha to determine rejection, we instead compare 1 minus the p-value to the 1 minus alpha quantile of the reference distribution, assuming the sharp null. And we'll talk about exactly why that ends up providing this resolution. But I'd say the big takeaways from this talk would be, instead of simply enumerating the randomization distribution of a seemingly natural test statistic, say the difference in means, if I want this robustness property under the weak null, what I want to do instead is to actually construct an asymptotically valid p-value under the weak null based upon that test statistic, and then enumerate the randomization distribution of 1 minus the resulting p-value. So I'd say, this provides this resolution. And furthermore, even if I'm only interested in average effects, if I'm only interested in the weak null, these pre-pivoted randomization tests provide an exact test under constant effects for free, while still having the same limiting power profiles as the asymptotic test whose p-value is being permuted. So from my perspective, modulo computation time, there's very little reason not to proceed with a test like this. It has the same limiting properties as the usual large sample test, but for free, except for Monte Carlo time to generate the randomization distribution. You also get exactness under the sharp null. So are there any questions before I dive into the details? I'm trying to look at the Q&A.
No, we don't have questions.
So Dominic?
I think
okay, all right,
continue.
Great. So Dominic, will you flag if something comes up?
Sure, I will.
Okay, thank you. Okay, so let's dive into some notation now. So there are n total individuals, n1 received the treatment, n0 received the control. These are going to be my treatment indicators. Really love that I can breeze through this slide with this group, that why I1 and why I0 are potentially multivariate potential outcomes. Tau i's are going to be the, of course, unobservable treatment effects. And tau bar is going to be the sample average treatment effect. And ultimately, under the weak null, this is going to be the estimand for which inference is desired. And further, xi are a vector of pretreatment covariates. So what I observe, I'll just say yizi is the observed outcome. Okay, implicit in this notation, I'll be assuming that SIFA holds. I'll let y of z be kind of the matrix of observed responses. And let me just define a few kind of functions. Tau hat, yz, and z is going to be the observed treated minus control difference in means for the outcomes. Okay, and furthermore, delta hat of x and z is going to be the observed treated minus control difference in means for the covariates. Now, I'm going to be proceeding this talk under the finite population model. And now in finite population causal inference, you can consider this as really inference conditional upon the properties of the study under investigation. So the potential outcomes under treatment and control for those individuals in addition to their covariates. So here, the probabilistic statements I make are arising solely due to randomness in the treatment assignment. Now, I know that, finite population model kind of divides opinions. So if you are of the mind that we should proceed under superpopulation models, I will say that these methods today naturally extend to various superpopulation formulations for inference for the pate, if I assume y and x are both random, or the kate, if I view x as fixed and view the potential outcomes as random. So I'm going to let omega be the set of allowed randomizations in the design. And so
Colin?
we'll really be focusing on two types.
Right. We have one question, I
yes.
think a clarification question about language. So we have
sure.
Are Fisher and style hypotheses referring only to those of a constant additive effect or all sharp causal hypotheses in general?
Oh, excellent. So I'm going to be focusing on, kind of the sharp null being no effect at all. And there are natural extensions to like constant effect models. But you're right, sharp nulls in general, I would view as more broad, like any null hypothesis that imputes the missing value for the potential outcomes. Yeah, it's a great question. Thanks. Okay. So I'm going to let omega be the set of allowed randomizations. So for example, in a completely randomized experiment, I'd say omega CRE would just be the set of treatment allocations where exactly N1 individuals are assigned. I should mention I'm just going to focus on two-arm experiments in this talk, but again, everything extends to the multi-arm case. It just introduced a bit more notation that I wanted to deal with in this talk. So we're going to talk about completely randomized designs. We'll also talk a bit about re-randomized design, if only because this was one type of design where up until this work, it was really unclear how to provide this exact and asymptotic conservative property, randomization tests that are valid for the weak null. So basically in a re-randomized design, we just discard randomizations that don't satisfy a certain balance criterion. The hope being that if the covariates are predictive of the potential outcomes, then by ensuring balance there, we should improve precision in the resulting inference. So I'll just introduce a balance criterion. So basically just takes as input kind of the covariates and gives as output an indicator of whether or not balance was satisfied. So there are various properties we need: closed, convex, near, symmetric about the origin. I'd say most natural balance criterion that exists in the re-randomization literature satisfy this property. So an example would just be Mahalanobis-based re-randomization, where what I do is kind of compute the Mahalanobis distance for that treated minus control difference in covariates, and I only accept randomizations where that Mahalanobis distance falls at or below a given value, as one way to try to exclude very imbalanced randomizations. Okay, so for now, I'm going to let Ty of Z and Z be a scalar test statistic. At this point, I'm not going to specify anything about it beyond that. It could be a function of the observed treatment assignment, the outcomes, and even the covariates themselves as desired. So the randomization distribution for T is then just written as follows. So I look over all possible values of omega. What would the observed outcome be, the observed matrix of outcomes be? That would be y of w in this notation. It could also be a function of w, that test statistic. So basically what I'm doing here for all possible assignments enumerating what the test statistics value would be, and that's going to give me this randomization CDF. Unfortunately, this is generally not known to us in practice because of its dependence on the missing potential outcome. So we generally do not know yi of 1 minus vi. So for that reason, I can write down this object, but I can't make use of it for inference in general without further assumptions. So now, suppose we want to test the sharp null of no effect at all, this Fisher's sharp null. So then under that null hypothesis, yi of zi, okay, the observed value for the potential outcomes, then imputes that missing potential outcome. So under the sharp null, I actually do have access to this randomization distribution. So I could say what I do know is yi of z, w, that's just the observed outcome, the observed matrix of outcomes, and then enumerate that over all possible assignments. I know that under the sharp null, that exactly equals this value here, which is the randomization distribution, which is why you get this exactness property for inference under the sharp null. Now, suppose instead that only the weak null holds, okay? But the researcher nonetheless uses this script pt, which is going to be my notation for the reference distribution, assuming the sharp null. So we're in this situation where only the weak null is assumed to hold, but the researcher nonetheless wants to use the reference distribution to which they would be entitled if the sharp null held. Then in general, of course, I can compute this reference distribution because this reference distribution really only depends on this y of z here, so I know these values, but it is not going to align with the true randomization distribution. So, and in fact, under the weak null, this P of t is a random measure. For different values of z, I get different yz, hence I get different values for script P of t in the first place, and it's not going to align with the randomization distribution. So it is ultimately this disconnect that can result in randomization tests assuming the sharp null being invalid even in the limit if only the weak null is assumed to hold. Now, to build towards kind of some desirable properties for ensuring validity under the weak null, let's just suppose that the randomization distribution converges weakly to some limit, say RT infinity, and furthermore that the reference distribution, assuming the sharp null, converges weakly in probability to some limit, pt infinity. So this, if you're not familiar with weak convergence in probability, just for all continuity points of the CDF, I get convergence in probability. And I need this just because it's a random measure. So I'm going to introduce a property called asymptotic sharp-dominance. So I'm going to say a test statistic t is called asymptotically sharp-dominant if for all t, I end up getting that these are left tail probabilities, so that the left tail probability of that reference distribution, assuming the sharp null, is bounded above by that true value under the randomization distribution in the limit. So then flipping things around, if t is asymptotically sharp-dominant under the weak null, then its limiting upper tail probabilities may be upper bounded by those of pt infinity. So what that would mean, it would actually give me this kind of robustness property of a Fisher randomization test. That would be saying that even if I use the reference distribution under the sharp null for inference, I know that those resulting p-values are going to kind of bound the true p-values. So the tail probabilities are going to bound the true tail probabilities from the randomization distribution. So if I could come up with a test statistic with this property, I would be good to go as far as giving inference that is exact under the sharp null and asymptotically correct under the weak null. So I'm just going to assume a few regularity conditions, nothing mind-blowing here, just need that the fraction of treated individuals converges to some constant t. I'm just going to say that the means and covariances for potential outcomes and the covariates have limiting values. And I'm further going to assume that bounded force moments, basically, for the potential outcomes and the covariates. And I'm not focusing on the weakest regularity conditions here. I believe that 2 plus delta moments is likely fine. There are just certain parts in the proof of what's happening with the reference distribution where fourth moments are very convenient. So now, basically, what I want to do now is think about the distribution of the treated minus control difference in means, just in general, its randomization distribution, and compare that with the limiting behavior of the reference distribution to try to get a sense of where is the disconnect coming in, and then what can be done to overcome it. So in completely randomized designs, we get this following kind of CLT result that under the finite population model, this vector of treated minus control difference in means and differences in covariates will converge to a normal with a covariance structure of the following form. I'd say the most interesting thing to note here is this v tau tau term, this kind of variance in the upper left. It depends upon the sigma tau. Now, the sigma tau is the covariance for the treatment effects, and hence generally cannot be identified. As a result, the upper left block here, v tau tau, cannot be consistently estimated. It depends upon sigma tau infinity. That said, many variance estimators exist that consistently estimate v tau delta and v delta delta, those other terms in that matrix, and furthermore satisfy a certain conservativeness property, such that the estimator minus v tau tau converges in probability to some value that is greater than 0 in the semi-definite sense. So an example is just the usual variance estimator in a, when I've got IID sampling from 2 independent populations. That would end up resulting in a variance estimator where v hat tau tau minus the truth converges in probability to sigma tau. So for that reason, I would end up having a conservative covariance estimator here. I want to compare this property now, or this kind of this behavior, to what we end up seeing under the Sharp null. So when we use the Sharp null, we use this reference distribution. This is just another way to write out what the reference distribution looks like when I do inference enumerating, assuming that the Sharp null holds. So in order to think about what happens asymptotically to any test statistic that is a function of the difference in means, let's think about the behavior of this conditional distribution. So this is in a sense thinking about what happens when I assume the Sharp null about basically the reference distribution, this conditional distribution for the difference in means and the difference in covariates. And by understanding the behavior of this conditional distribution, we will then be able to understand the behavior of any test statistic that's a function of the difference in means. So this is a theorem by Wu and Ding. Say we also get, under the conditions I've laid out, convergence weakly in probability to a mean 0 Gaussian with the following covariance structure. Now, obviously hard to absorb everything here. What I want to focus on is just a few discrepancies between the two results I've shown so far. So looking first at the limiting covariances for the randomization distribution and comparing that to the limiting covariances for the reference distribution, I see that in the upper left, for example, compare v tau tau to v tilde tau tau, I end up seeing a discrepancy here in terms of the limiting covariances governing those random variables. The reason being, in a sense, the p's and the 1 minus p's here have been switched for the true randomization distribution versus the reference distribution. And I also have this subtraction here. The consequence is that generally v tilde does not equal v. And as most test statistics one would use when desiring inference for the weak null are going to be functions of the treated minus control difference in means, they're really just going to be push forwards of these measures that I've just talked about. So as a result, the reference distribution is not going to align with the actual limiting distribution, with the exception if the Sharp null holds. So this is the reason that in general, you have to be careful with which test statistic that you end up choosing. I'll now dive into some details for thinking about generally, how do I construct a test statistic with the desired robustness property? Now, I would say most test statistics for the weak null can be expressed in the following form. Okay, I'm basically going to take some function of the treated minus control difference in means. Okay, that function might depend upon some nuisance parameter, say psi hat. And I'm going to say, put some conditions down on this function and on psi hat. So I'm going to say this function is continuous, quasi-convex, meaning that it has convex level sets, and it's non-negative in mirror symmetric. So I will be looking at kind of two-sided inference here. But to say anything like the absolute difference in means, Mahalanobis distance, most of the usual candidates you consider can be written in this form with a function that satisfies these properties. So furthermore, this nuisance parameter psi, which will also often be like a variance estimator, but it could be other things as well. I need that basically this nuisance parameter basically has a limit in probability, both under the true randomization distribution, which is what I'm laying out here, and also under the reference distribution. And these limits in probability can be different, they just need to exist, okay? So we're further going to proceed using covariance estimators such that I have this nice conservativeness property, that if I look under the true randomization distribution, then my variance estimator satisfies the following limit in probability. So basically, it's going to be consistent except for that upper left that pertains to kind of the covariance for the difference in means of the potential outcomes. And it will then be, you know, kind of conservative in general, this delta being non-negative definite. Okay, and furthermore, I'll assume that under the reference distribution, this covariance estimator is consistent. And that ends up being true of most any covariance estimator that has this conservativeness property. They generally have the property that if treatment effects are constant, then the covariance estimator is consistent rather than conservative. So this is, again, not a strong assumption and is, you know, satisfied by most any common variance estimator deployed in practice. And again, just want to reintroduce these balance criterion that will be underlying our use of re-randomized designs. So I'm only going to accept certain randomizations that satisfy certain balance conditions. So test statistics of this form need not satisfy asymptotic sharp dominance when the weak null holds, but the sharp null does not. So as just, you know, one of our motivating examples is the treated minus control difference in means. And if outcomes are scalar, and I just use root n times absolute tau hat in a completely randomized design, the true distribution and the reference distributions, well, they both go to half normals, but with different dispersion parameters. And it can be the case that the true dispersion parameter is larger than the dispersion parameter of the reference distribution. If that's the case, you are going to get anti-conservative inference coming out of this. So then what can be done to establish sharp dominance? And ultimately, this is where the role of prepivoting comes in. So prepivoting was introduced through a few seminal papers by Rudy Baran in the late 80s. It's the act of transforming a test statistic by an estimator of its distribution function. So come up with a sample-based CDF that estimates the CDF of the test statistic, and then apply that to the test statistic as a transformation. So Baran's original use of prepivoting was in the context of the bootstrap. And what he realized is that if I look at applying a bootstrap CDF to a test statistic, I can, through bootstrap iteration, attain higher order corrections to the level of tests and to confidence intervals. Okay, so we've mainly focused on higher order improvements in the bootstrap through this use. But we'll be using prepivoting for a different reason, to restore first order correctness to tests of the weak null, to randomization tests of the weak null. So here is just going to be kind of the formulaic description of what this transformation looks like. I will try to walk through it to make it make a little more sense. So if I start with the test statistic, say Ty of z and z, that satisfies this general form, some function of the treated minus control difference in means, let's consider the following transformation. So basically, this gamma mu sigma is just going to be like kind of the Gaussian measure of a set B with these parameters. So what I am imagining doing is thinking here, okay, let me think about a multivariate normal with mean 0 and covariance equal to v hat. So let me imagine that my estimator is actually the true covariance just for this computation. Let me think now, what is the measure ascribed to the area, kind of that area of that multivariate normal, such that this function value falls at or below the observed value for the test statistic, and that balance is satisfied, divided by just the probability under that v hat, the balance is going to be satisfied. So it's just that conditional kind of the conditional CDF, kind of a CDF for this test statistic, kind of generated by a Gaussian approximation, conditional upon balance being satisfied. So yeah, just stated in a few different ways to try to wrap our minds around it. So if I imagine psi hat and v hat are fixed, and I take A and B to be jointly multivariate normal with a mean 0 and a covariance v hat of that form, gy of z and z represents kind of that f psi push forward measure of A given phi b equals 1 evaluated on that set. So that would be more of a probabilistic interpretation for what's going on here. But really, when you stare at that formula, you realize it's just 1 minus the p-value of a large sample test for Neyman's null, with ty of z and z as the test statistic. So I'm approximating the limiting distribution under Neyman's null by replacing the unknowable v with its consistent upper bound, v hat. And I'm then proceeding calculating, say, 1 minus the p-value under that, using that estimator. So it evaluates the CDF of the large sample approximation at its observed value, which is just 1 minus the p-value. So now, usually, when we just do Neyman style inference, we would stop there. I've got my large sample p-value. I'm going to conduct inference and decide to reject the null or not based upon whether or not that p-value just exceeds alpha. What we'll do here is plug that 1 minus that p-value in and use 1 minus that p-value as a test statistic, assuming the sharp null, and generate that reference distribution. So that's precisely what this reference distribution is doing. I'm using that 1 minus that p-value, that large sample p-value, as a test statistic and enumerating that reference distribution. So of course, the reference distribution and the randomization distribution are not going to align exactly. But suppose that I decide to use this as my test of the week null. So I decide to reject while attempting to maintain the type 1 error rate at or below alpha if the following holds. If the observed value for my test statistic is above, say, the 1 minus alpha quantile of this randomization distribution. Okay, and so the main theorem is that this ends up satisfying asymptotic sharp-dominance. And we'll kind of walk through kind of what exactly this all means here. So under the weak null and under our regularity conditions, then the true randomization distribution for g of y, z, and z, that's just 1 minus the p-value, converges in distribution to a random variable u tilde that is stochastically dominated by a uniform distribution. So for all values t, the CDF for this random variable is greater than or equal to t, which means it is stochastically dominated by a uniform. Furthermore, if I think about the behavior of this reference distribution now, the reference distribution actually converges weakly in probability to a uniform. So the true randomization distribution is stochastically dominated by a uniform. The reference distribution converges weakly in probability to a uniform. So as a result, the reference distributions of our tail probabilities have bounded those of the true but unknowable randomization distribution. So the consequence here is that, first of all, because I'm doing a Fisher randomization test, I still get this wonderful exactness property if the sharp null holds. For any n, I get this property, okay? That I get size alpha inference. But under the weak null, I furthermore get the type 1 error rate has been controlled when using this reference distribution that I really should only be entitled to under the sharp null. So again, that conservative inference is just a fundamental property of inference under the finite population model. So this kind of accomplishes the task. I now have a single procedure where it is exact for the sharp null and asymptotically conservative for the weak null. So in the time remaining, we'll just go through a few examples just to first show that this actually precisely recovers the known kind of corrections that exist in the literature, and furthermore provides a whole new suite of resolutions, a whole new suite of test statistics for designs where, as of yet, we don't know how to do this, how to provide these robust randomization tests. So as we talked about, root n tau hat is not sharp dominant. If I think about what happens when I apply Gaussian prepivoting here, well, g, y, z of z is just the following: 1 minus 2 times, this is the standard normal CDF, negative root n absolute tau hat over v hat tau tau to the 1/2. So that's just the probability of, say, an absolute standard normal being less than or equal to a given value t, evaluated at that value there. So what we want to observe here is, and it's actually pretty straightforward to show this, is that when I think about enumerating this reference distribution for this statistic here, and think about what that reference distribution would look like, it turns out that it actually has perfect rank correlation with the usual studentized test statistic. So when enumerating that reference distribution over all possible omega under the assumption of a sharp null, the prepivoted test statistic has perfect rank correlation with the studentized test statistic. So what that means is that the two randomization distributions thus furnish identical p-values. So the reference distribution of the prepivoted test statistic will furnish identical p-values for any z, for any y, as that attained through studentizing. And studentization in CREs has been shown to provide sharp dominance. There's a nice comment of a paper by Peng Dean, by Lowe, Richardson, and Robbins that talk about this. So this is a known resolution. We'll move on to another test statistic where, I'd say up until this point, we weren't really exactly sure how to do it, how to provide this resolution. So suppose, again, we have a completely randomized experiment. But instead, suppose I've got multivariate potential outcomes. And I want to consider, say, the following very natural test statistic for the null hypothesis that, say, the weak null equals 0 for all individuals. The average treatment effect equals 0 for all of the outcomes, rather. So that would just be looking at the max t statistic. Okay. So this is not asymptotically sharp dominant once I go from d equals 1 to d greater than 1. The reason being is that the true randomization distribution depends upon the correlations embedded in z, which is that limiting covariance for the true randomization distribution, whereas the reference distribution's limit depends upon the correlations embedded in z tilde. And after studentization, those correlations can still be different. So I can still get anti-conservative inference if I just use this test statistic. So what Gaussian prepivoting does is it imagines that I take random variables a1 to ab, normal, with 0 and with covariance v hat tau tau, and I just compute the probability that, say, absolute aj over v hat tau tau jj to the 1/2 falls at or below the observed value for the test statistic. Again, just using this large sample Gaussian approximation and computing 1 minus the p-value under that approximation. And that ends up providing the resolution there. So we'll wrap up now with just one more example, looking at Mahalanobis-based rerandomization. So in Mahalanobis-based rerandomization, we accept a randomization if the Mahalanobis distance for the treated minus the covariate difference in means between treated and control falls at or below a given value c. So let's say that I've got a univariate outcome and I consider the studentized test statistic. This might seem like a very natural place to start. The studentized test statistic, after all, is sharp dominant for completely randomized designs. Maybe it's the case that studentization is the important thing here. Maybe studentization provides a resolution. So this is just what the transformation Gaussian prepivoting looks like when applied here. It's just using that v hat, my conservative covariance estimator, to form an asymptotically conservative p-value. And then, 1 minus that p-value is what's being shown in this equation here. So unless the balance criterion is vacuous, what ends up being the case is that the studentized test statistic and the prepivoted test statistic no longer have perfect rank correlation when enumerating their reference distributions. So I'm just going to show a little simulation to show that things can go haywire with just studentizing, but that it's corrected after pre-pivoting. I wouldn't worry too much about the parameters here, so maybe we'll just skip over that. But I'm just going to do a few simulations, both assuming the sharp null and only assuming the weak null. And I'm going to say 20% receive treatment, 80% receive control, and I'll consider a re-randomized design where I end up accepting a randomization if its Mahalanobis distance falls at or below 1. So I'm going to compare inference using 3 randomization tests: the absolute difference in means unstudentized, the absolute difference in means studentized, and after applying Gaussian pre-pivoting to the absolute difference in means. So, and we're going to compare performance also to the usual large sample tests. So let's start by looking at the rows corresponding to the sharp null. And so we see here, of course, the benefits of using a randomization test. If the sharp null holds, then this is just modulo some sort of Monte Carlo error. We get exact inference, okay? So the desired type 1 error rate here is alpha equals 0.1. The randomization tests, except for Monte Carlo error, accomplish that. Whereas the large sample test here, especially at n equals 50, can be very, very far off, can be anti-conservative relative to its desired size. So these are the benefits of a motivation for using a randomization test in the first place. Now let's consider inference under the weak null, n equals 50 and n equals 1000. So what we end up seeing happen here is that studentization and no studentization continue to provide anti-conservative inference under the weak null. So the randomization tests that use either the treated medicine control difference in means or that studentized are anti-conservative, and that anti-conservativeness consists asymptotically. The reason being they aren't doing pre-pivoting. Whereas this is the pre-pivoted randomization test, and we see that we end up getting that conservative inference under the weak null to return. The other thing you want to note is that as n increases, you see that kind of the performance of the test kind of aligns with the performance of the large sample test, which should make an awful lot of sense. I'm actually using the p-value from a large sample test as my test statistic when conducting inference. And so that reference distribution converges to a uniform, whereas the randomization distribution has its usual properties of the true p-value. And you compare that with what you do in the usual large sample inference, where you just compare, in a sense, to the quantile from the uniform in the first place. So the performance in terms of power profiles aligns between the pre-pivoted randomization tests and the large sample tests as well. So to wrap up, I'd say pre-pivoting provides a general recipe for restoring asymptotic validity to randomization tests under the weak null. I would say it subsumes studentization in situations where studentization itself would provide a resolution. It also highlights the importance of using a randomization distribution of a pivotal quantity. You gotta make sure you have a pivotal quantity. And what's more pivotal than taking a p-value in the first place? So the general structure here kind of extends very naturally to other designs, paired, blocked, finely stratified, etc. And it extends naturally to studies with more than 2 treatment arms as well. I'd say thanks very much for having me, and here are a few references.
All right, thank you very much. Sorry, Chingguan. So thank you.
Okay, sure. Yeah, let's switch to our discussant, Tirthanker. So we don't have. Yeah, Tirthanker, it's your turn now. Let me.
Yes. So I'll just share my screen. Okay. Okay. Thank you very much, Dominic, Chingguan, and Yin for giving me this opportunity, and thanks to Colin for delivering a fantastic talk on an outstanding paper. I really think this paper is going to be amongst the landmark papers, which really connects the randomization test with the weak null hypothesis, and in terms of setting up a general recipe for doing these kind of things. So I would just like to recap some of the main points which Colin mentioned pretty clearly during his talk. So first of all, whenever we talk about Fisher randomization test, we always talk about the key advantage that it can be conducted with any test statistic, and it's always valid under the Sharp-Null hypothesis. When we talk about the disadvantages, we immediately think about its applicability in the context of Neyman's null. So when we started I started teaching some of these topics with Don Rubin at Harvard, and quite often these questions used to come in from students, like Fisher randomization test is interesting, but the sharp null isn't quite. So isn't the test of average equality of averages more exciting? And does the randomization test work under such kind of hypothesis? So this was a question which actually bothered us for quite a while. And of course, at that point of time, we had a very brilliant student, Peng Ding, whose work Colin mentioned. So Peng and I discussed this quite a few times. So we tried to come up with some ideas. And so initially, we thought that we could probably come up with a solution for the one-way type of ANOVA setting, where if we use the usual F statistic to perform the Fisher randomization test, that may not be a valid test for the Neyman's null. So we came up with a new test statistic called X squared, which was some sort of a studentized test statistic, taking into consideration the heterogeneity, possible heterogeneity in the data, in the potential outcomes. And then we found its asymptotic distribution. And so the key result, which really helped us use that statistic for the Neymanian null, was the fact that it was asymptotically dominated by a chi-square. So, and as Colin mentioned, there were similar work done by Lu et al. And then Wu and Ding, of course, did a much better job in 2020, when I thought that that was a generalization of many of these results. But still, I think most of these work were done on a case-by-case basis. So we always thought that we have to think about a specific design, and then we would have to think about how to deal with that particular scenario in terms of using asymptotics wisely to come up with a statistic which is also valid for Neyman's null. So this is where I think Colin made a major breakthrough. So all of our work earlier has been incremental. And I think this paper is going to make a major impact, because whenever we think of literature which eventually kind of makes a huge impact, are those which are at the top of the pyramid, right? So they deliver results of which most existing results are special cases. And that is exactly what this paper is doing. So Colin has come up with a unified framework, which provides a very general recipe for finding test statistics that are exact under the sharp null and are asymptotically conservative under Neyman's null. Specifically, I think there are 4 points which need to be mentioned. So first of all, it provides valid alternative procedures to existing solutions. It provides solutions to new experimental design studies, which are not yet studied. And as Colin mentioned towards the end of his talk, it busts the implicit myth that if you use a smart studentization for each specific case, you could solve this kind of a problem. And Colin indeed shows that if studentization can provide a resolution, it would be a special case of the proposed framework. And once again, I think this revolves around the key concept is finding this asymptotically sharp dominant test statistic using Gaussian prepivoting as the primary tool. So once again, it has all the hallmarks of a great paper. So it is breakthrough, it is elegant, it is deep, rich, insightful, educative, tells a very nice story from the beginning to the end. And this is something which really makes a paper, I think, a fantastic paper to read. So amongst the major mathematical tools, of course, we have finite population asymptotics. And to all young researchers, I always would mention this: if you want to work in this area, you should read the paper by Shinran Li and Peng Ding, the JASA paper in 2017. It provides us with a very nice foundation of finite population asymptotics. But then this was, I think, really the piece of work which was ingenious in this particular context, bringing in the idea or the notion of prepivoting, which essentially is transforming a test statistic by an estimator of its distribution function. So this was brought in and combined with the ideas of finite population asymptotics, and the results are of course very deep, and the proofs are extremely rigorous, but I think these are probably two pillars on which all these things stand. So just a couple of thoughts. And this question, I think again, I've been asked, and I have also asked to several people. So if we just go back to Fisher's sharp null, we know that one of the strengths of FRT is the fact that we can use any test statistic as to conduct a valid Fisher randomization test. So should we really care about the choice of test statistic? And of course, if so, how should we do that? And whenever I've asked this question to Don Rubin, he says, choose anything that makes sense. Fisher didn't bother, why should we? And I remember when actually Colin was an undergrad student at Harvard, he was also amongst those brilliant guys who occasionally asked this question, and I didn't have an answer then. And I don't have an answer at this point of time as well. And I'm asking this question once again because recently in this JRSSB paper which just came out, we found out some I would say, results which are not very intuitive, that studentization may actually be bad for the sharp null in finite samples. This problem is resolved asymptotically. So I was just wondering whether there is any connection to Colin's work and the negative effects of studentization. So that is potentially something which I would like to think about. So that's all. And once again, thanks to everyone. Thanks to Colin. And on a great day for causal inference. Thank you.
Colin, would you like to respond to Tirthanker's discussion?
Sure thing. Yeah, I just say thank you very much, Tirthanker, for the kind words. I would say that some of the questions that you bring up at the end are very interesting. In particular, this issue with studentization, and you're probably referring to, there are these issues where after studentization you don't get an effect increasing statistic, which is kind of odd. And right. In fact, I'll just plug that Xinran Li is giving a talk in this seminar in a few weeks, and he's got this wonderful paper about kind of a different approach to thinking about other interpretations to tests of the sharp null, just talking about tests of, say, bounded treatment effects, which provides a really nice complement to kind of the approach that I took here. In terms of ways to resolve these issues in this context, I do think that's open at some level. Like, you need prepivoting is going to involve a covariance estimator, at least as I formulated Gaussian prepivoting. There are some interesting things that arise in thinking about prepivoting in general, that what you really see is the essential ingredient is to have kind of a p-value that is like, it's going to be asymptotically correct under the sharp null and conservative under the weak null. And the typical way that we thought about doing that is based upon Gaussian approximation. But when you start thinking about it as p-values, you can realize there are probably other sampling schema that can get you p-values that satisfy these properties. So we have some follow-up works actually looking on the use of various bootstrap schema to satisfy this. So I'd be curious to look to see if any of these alternative ways to actually pivot beyond just using like studentization analytically still have these issues that you're talking about. But I think that's super interesting, and I don't have a clear answer yet, but you've given me a few things to investigate.
Wonderful. Thank you so much.
Okay, we still have 5 more minutes. There are no open questions in the Q&A at the moment, but I'd like to encourage the audience to ask any questions they may have. I actually do have a question for Colin, which is sort of a follow-up on Tirthanker's first question. So when you apply the sort of the prepivoting transformation, does that affect the power of your test?
Okay, so what you end up getting is exactly the same, under Pitman alternatives, you get the same exact performance as whatever p-value you've permuted. So, like the ingredient, you start with a large sample test, right? And then you look at the randomization distribution of that p-value. It ends up inheriting the power performance of that, of the test for the name and null. So, I mean, it would affect it relative to not pre-pivoting, but I would say if you see a discrepancy in the power profiles, that could be indicative of the fact that whatever alternative test statistic is under consideration might not actually be valid under the weak null in the first place, which was the point of applying the transformation.
I see. So you lose a little bit in that regard, that because we now have a test that's also valid for the weak null. We also lose a little bit of power when we just want to test the sharp null. Did I get it correct?
I also think there's, I mean, potentially, yeah. But if you've lost power relative to the sharp null, that means that test for the sharp null doesn't have this nice property.
Of course.
Yeah. I mean, there are also, I feel like some open ways to think about combining sharp and weak nulls and other approaches, like sequential hypothesis testing. If you test hypotheses in order, start with the sharp null, or start with the weak null. If I reject, great. If not, check out the sharp null. There are ways to actually do that maybe you could combine some of these tests together, and maybe they would have interesting kind of performances.
Okay. I think we may have a question.
There's one in the chat. Yeah. Can you talk about generalization?
Oh, yes. I see it. I see it. So I'll read the question. So the question is can I talk about generalizations to other randomization schemes beyond re-randomization or complete randomization? Definitely. So, moving beyond these, the key ingredient for applying Gaussian pre-pivoting is really just having a covariance estimator that satisfies those required properties. And so if you've got I guess you need asymptotic normality, but you also need the covariance estimator should, under heterogeneous effects, be conservative, under constant effects, be consistent. And then, you have to combine that with some of the conditions that I made on the test statistics, because you need to somehow translate conservative covariance estimation into conservative p-values. And so there's a theorem called Anderson's theorem that is about concentration of normals with different covariances that ends up allowing you to do that. Say, okay, I've got a conservative covariance estimator, therefore I have a conservative p-value. It's not always true, but it's true under a set of assumptions that many test statistics hold. So, if I've got any other scheme like paired experiments, block randomized experiments, where I have a conservative covariance estimator, that's the crux of what you need.
I think this is perhaps a good time to end our seminar today. Next week, please give me a second. This is not showing correctly. Okay, so next week we will have 2 shorter talks. Sorry about that. First talk will be by Juan Correa from Columbia University, and I'm not going to test my pronunciation of Spanish. Juan will talk about generalizing the effect of soft interventions. The second talk will be by Nicola Gnecco from University of Geneva on causal discovery in heavy-tailed models. So I hope I'll see everyone next week.